Another day, another problem. Today we'll have a look at the 2020 Advent of Code Day 14 problems. Once again, we're going in completely blind. Let's hope we can make a better fist of it than yesterday's. Day 14. We need help again. Our poor fairy. The computer system that runs the port isn't compatible with the docking program, blah, 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 blah. The Seaport's computer system uses a strange bitmask system. The initialization program, your puzzle input, can either update the bit mask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. Mem8 equals 11 writes a value 11 to memory address 8. Okay, the bit mask is always given as a string of 36 bits, written with the most significant bit on the left and the least one on the right. Current bit mask is applied to values immediately before they are written. 0 or 1 overwrites and an X leaves it alone. Okay, so you set the mask and then you do some writes. The mask it specifies will overwrite 2 bits in every written value. So every time you write, you'll always get a 1 there and a 0 there, regardless of what goes in there. The program then attempts to write the value 11 to memory address 8. So 11 looks like that. The mask gets applied, so that 1 becomes a 0, and that 0 becomes a 1. So instead you get 73. Okie dokie. This time the mask has no effect, as the bits it overwrote were already there, and then you try to write 0, but instead you get that. Okay. To initialize your fairy's docking program, you need the sum of all the values in memory after the program runs. Everything starts at 0. In the above example, only 2 values in memory are not 0. 101 and 64. Oh, because that one gets overwritten twice. Yep. So at the end of the program, you just have 101 and you have 64. Yep. Making up 165. Execute the program. What do you get? All right. Let's grab the input. Save. Okie dokie. Let's have a look at it. Page 14. Oh, okay. So it's about 500 lines long. So we set mask, do some writing, set the mask, do some writing, set the mask, do some writing. Okay. That doesn't seem too bad. That doesn't seem too bad. I think we can manage this. Okay, let's start by figuring out how we're going to parse this thing. So we'll get the contents of the file and break it into lines maybe. We'll do it in a fairly ad hoc sort of parsing. We won't try to do anything too fancy. So we get the lines and then we'll go map parse lines, which each of those. Call that program. Now the program, or each line, will represent as, so either setting a mask, an instruction is either setting the mask to some, we'll just keep it as a string, or we're going to write to a particular address, which we'll use an integer for, and we're going to get another one. So for example, that second instruction, mem 17353 equals 91550 would be 17353 there, 91550 there. So parsing a line is just turning a string into an instruction. And let's do it. Because it's so sort of rigid, we don't have to be too fancy with our parsing. We'll just say if, in fact, we can cheat a lot if we're willing to not be too generic with our parsing. We can say so there's our line. We can say if if the line starts with mask equals, right? So if tech for line equals mask, then we need to just drop the first 7 letters, and we get mask, mask, drop 7 from the line. Otherwise, it must be one of these memory writing ones, in which case we can drop the first 4 lines, and that'll take mem and the first bracket out. So we'll do this. This is pretty ugly, but we're in a hurry. We can say drop 4 from the line. Then we can go take while is digit. Yeah, why not? So we'll go let the memory address be take while is digit drop 4 line. Is digit is in here. And then we can cheat even a bit further. Just look for the equals. By splitting on, so split on the equals. And I think we can just drop that character and read it in. So the value is just, got to read as well. We go read. So I think, as hideous as that is, it will work. Right, A, B. Didn't like that. It doesn't know how to print it out. Okay. Right, let's run that, see what we get. Oh, that's good. Good. Let's try again. Print it out 1 per line, and then we get this. And if we compare that with our input, that looks right to me. Okay, that'll do for parsing. Now for executing. So let's think about what state we need to keep. We just need to keep track of the state of the memory and the state of the mask. So we'll say our execution state E is just pair. We won't even give it a proper type. We'll just say an execution state is a map. So this is the memory. Memory is a map from integers to integers. And we'll also keep track of the current mask, which we will represent as it's a bit hard to know what to do there. We'll just keep it as a string for now, since we don't know what to do. For that, we're going to need data.map. No, we're still good. We're still good. So executing an instruction. Execute instruction takes the current state and produces a new state. Now executing a mask instruction is going to be very easy with this representation because it's just it's just overriding the mask we had before. So it's just that. Now executing the writes is going to be a bit trickier. So writing address value given the current memory. M is not a great thing because it could stand for mask or memory. We'll call it mem. Mem. And mask. Now the tricky bit is not updating the memory, it's computing the right value to put in there. So we can, it's going to be m.insert. We're going to write to memory at address A, and we're going to have to compute the value and the mask to memory, and we keep the mask the same. And then now we've shuffled the hard work into here. We're given an int and a mask. How are we going to compute what the updated value is? So we can ignore any built-in ways of doing binary and just sort of do it ourselves for the fun of it. So let's leave that undefined for now and write a few backwards and forwards to binary functions. So int to string, and this is going to give us a number. We're going to take a number and turn it into a binary string. And we'll do that as follows. So 0 is going to be the empty string, and anything bigger than 0, we'll do this. We'll take the mod, we'll divide it by 2, see if it's odd or even. So we can do it like this. If n is even, then 0, else 1. And we just stick that on the end of int to string and over 2. Now this will give us the string backwards. So maybe we'll do this and reverse it all at the end. Okay, let's give that a whirl. Int to string 12, 10, 11, 28. That's not what I expected. And in fact, it looks wrong. Let me think about this for a minute. 1, 2, 3, 4. Oh, something's gone very bad there. What have I done wrong there? Oh, look. Oh, that's a subtle error. There we go. That's better. 256. That looks good to me. And now let's go in the other direction. String to int. String to int is going to go. Now this is not too bad. Actually, before we get onto that, let's address one little problem, which is 0, which gives us an empty string. What I actually want to do is pad this out to 36 bits to make it line up with the other one. So we'll go replicate to do this a bit noisier. So let the reversed string be that, and then we'll replicate length r 36 minus length r 0 strings and stick that on the front of r. And now we should get always 36 bits. 36, beautiful. So now let's go in the other direction. Now here we only need to handle 36-bit integers, but we can make it generic just as easily, so why not? And this should be just a matter of going, let's fold over the string. When you get a digit in, you just take the accumulator, shift it over by 1, which is multiplying it by 2, and then adding conversion of the digit into a number. And we start at 0, and I think that's it. To int 12. Yeah, that looks right. That's 10. And now if we go string to int to string, anything, should get the same number back. That looks pretty good to me. Okay, so now with these in hand, we can have a look at computing this mask. So we've got our number and we've got our mask. And what I'm going to do is I'm going to convert that number to a string so that I can effectively line up the mask and the string. So now I can go zip. So imagine we have a mask, right? XXX110X. And we have a number like having converted it to a string, and it looks like this 1101. We're just going to line them up and combine them like so. So the new string S2 is zip with F. I'll define F in a minute. S and mask. Mask first. And then we just turn that string back into a number, string to int s2. Now f takes the mask digit, and the real digit. So if it's x, you don't do anything, you just leave it alone, d. If the mask says 1, throw that away and say 1. And if the mask says 0, you throw the digit away and say 0. And everything fails. I think I've forgotten how zip width is defined. Yep, that's better. Okay. So now I should be able to go compute. Now, this will only work if they are both strings of the same length. So it's important that int string returns strings of length 36, and my masks are always length 36. So to test this, it's going to be a bit of a pain actually. I'll just steal one out of the input. Let's grab that one. And now if I go compute 1 in this mask, what do I get? Oh, that's a shame. That's a bit annoying. Convert that back into a string so we can have a look at it. So I should get the same, right? Basically all the bits I've got are thanks to the mask. But if I say now 2, and the last digit of 2 is a 0, but it should get clobbered with a 1. And if I write 3, I should get another 1 in the second last spot. Oh no, the mask is overriding that. But if I do 7, the third bit from the right should become a 1. Yeah, that looks pretty good to me. So now the question is, run the program. Hey, we've got to run the program. So we have a way to execute one instruction. Run program just takes a list of instructions. And we can just produce an execution state at the end. In fact, we'll take an execution state. We'll take the initial one. So this should just be a matter of folding, execute, just go flip it the other way around, flip execute, starting with the initial state, which is going to be an empty memory and a mask of 0. Mask of 0, and fold that over the instructions, I think. So if I now go, well, let's just do this. Let's not print that, let's run it. Run program. Oh, I've lost the plot. What am I doing? That doesn't go there. It's E. That goes up here. Run program. And this is going to return an execution state. And let's just print it out. It's going to be a bit hideous, but it looks like it's done something. We can check just before we submit our answer, we can have a quick squeeze at this. And we can look at like what's in memory position 3272. 3272 is this number. That number. And we can go int to string on that. And that gives us that. And the mask at that last stage was this. So if I print that, and we look at them and we sort of line them up, we can see what should have happened. So for example, the first bit, no, second, they kind of line up already. Oh, of course, because we've applied the mask, but what we've got to look at is actually int to string 2146. Right, this was the number we attempted to write, and the mask, so if you sort of add this way, look at that, apply that, we should get that. And it looks like that's what happened. All right, that looks good to me. So now we've got to add them up. And it should be just a matter of getting the memory. So this is the final memory and the final mask which we don't really care about. And we just go m dot, I think it's lems, to get all of the values out, and we just add them up. And that, hopefully, is the answer. All right, let's carry on. Now, for some reason, the Seaport's computer system still can't talk. It must be using version 2, and here we were doing version 1. Version 2 chip doesn't modify the values being written at all, but we just did all that work. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. 0, leave it alone. 1, clobber it with a 1. X, you float. Okay. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, it will take on all the values at once. Well, that's a bit scary. For example, consider the following program. So this is going to write 4 addresses at once because it's got 2 X's. When you do the first one, it applies the bit mask. 4 bits over. Yes, 4 bits are overwritten with 2 floaters. So actually you get 4 addresses getting written. Next, the program is about to write memory address 26 with a different bit mask. So it has 3 floaters, so 8 bits, 8 memory addresses get written. Now, the thing that scares me about this is that if the number of addresses written is 2 to the power of the number of X's. So if there are any masks that have a lot of X's, I'm very worried. That did not do what I wanted. I wanted to count how many X's there are. They don't seem to be many that are that big. We can have an actual look if we wanted, I suppose. If we're worried, and I am a little bit worried, we can go for each instruction in the program. If it's a mask, and let's just print it out. If it's not, just don't do anything. Let's just run that. So it's just printing out all our masks. Now let's print length filter is an X. N. Well, I'm not seeing any 2-digit numbers, so I'm all right. So I think we can do this in the naive way, which is just to write to all the addresses as we go along. We don't need you anymore. So now let's change the program so that it does what it needs to do. So we need to change the way masks are applied. Okay, so this function's got to change. So now when we have a number, which is now an address, not a value to be written, when we have a number, we need, where are the rules? If the mask has a 0, if the mask has a 0, you leave it alone. So 0 needs a D instead. If the bit mask is a 1, it's a 1. So that's actually the same as what we've already got. If the bit mask is X, then it needs to float. Now, what are we going to do with you, Mr. Float? So what actually has to happen here is I'm going to put an X in to represent a floating bit, and this is going to have to return a list of addresses instead of a single one. And that means string to int is going to have to be a bit different. So string to int, I might make a second version of string to int. So string to int with floats. I know int float sounds a bit strange, but we'll deal with it. So this is going to return now not a single number, but a lot of numbers. And what we'll do is This is a bit tricky. We can do this in a kind of nice way. So we've got our string. We can do it in a sort of loopy way. If we get nothing, then you just get a single value 0. Okay. If you get something, if you've got a bit, call it D, and a string, or the rest, we can do this. So let's compute the rest. String to int float D's. And then, depending on what D is, if D is 1, oops, D is 1, then we should just go, oh no, I'm thinking about this wrong. What I should do here is really abuse our powers by doing this and sort of doing it by magic. So if you get 1, then what you do is you have to stick this 1 on the front. Maybe I haven't thought this through very well. Because what I've done is I've calculated the rest of the value from the right-hand side on. What I really want to do is do it in the other direction. It makes it a lot easier. So I'll do that. So I just want to go 2 times rest plus 1, 0. It's the same thing, but plus 0 if you like. And for a floating bit, we're going to give 2 answers. We're going to give, I'll just do this the other way, make it look a bit nicer. We're going to give 2 answers. It's going to be, it's going to be both of those, right? It's going to be 2 times rest plus 0 and plus 1. Now the problem with this is that it's kind of wrong because it does the bits in the wrong order. Let's just see if it works at all yet. Nope, didn't like that. Oh, I haven't finished with you. Let's deal with you later. Yeah, we'll deal with you guys later. Yes, yes, yes. Okay, so that worked at least. Now if I go string to int float 1100. Yeah, I had a feeling it would give me 3 because 3 is backwards, but that's okay. That's easy to fix. We'll just reverse the string first. Ta-da! So that's 10. But with a floating bit, it's 10 or 11. And with a floating bit there, it should give 10 or 12. Sorry, 12 or 14. So hang on, that one was wrong, wasn't it? Yes, 1100 is not 10. This is 10. That's not 6. Oh, look, we're losing a digit, that's all. Why? What's going on? I'm losing a digit. So let's see here. One, 2, 3, 2. Is it only 2? Is it something about zeros that are not working? Why would that be? Let's just walk through how 110 worked. 100 did not work. So we're going to reverse the string. We're going to have 001. That doesn't match. We're going to be there. we're going to do that, which is going to pass in the rest, so 0, 1. D is going to be this, so we're going to go 2 times the rest plus the 0. Yep, that sounds reasonable. So then ds, so when ds is 0, oh my god, I've done the same thing again. The perils of the prime. Okay, this looks a bit better. Let's try those other ones again. 12 and 14. So this should give the numbers 12 through 15. Yep, that's good. And the more we do it, the more numbers we should get. That looks pretty good to me. All right. So now we can go and try and resurrect what we've got up here. So now we've got this. A compute has changed type. It no longer returns a single number. It returns a lot of numbers. So we need to change things here. So mask, still set for mask. That's fine. When we write now, we need to fiddle with this. So what we need to do now is, let's just do we'll do a fold, right? So the new memory is going to be fold. We're going to fold over, starting with the old memory, we're going to fold over all of the addresses. So let's compute those. The addresses is going to be compute the original address, the one that was in the program, fiddled with the mask, and then the new memory, we're going to fold over all those addresses, and then for each address, we're going to do this. Let's write that. m.insert at that address. Oh, I'll call that a prime at the risk of making yet another mistake. We've got to insert at the fiddled address the value v into m. And then we return the new memory and the unchanged mask. Oop, didn't like that. Really? What's wrong with that? Let's see what it says. Couldn't match type in with, oh, I've got these in the, I think I've made some mistake in the ordering here. What's the type of folder again? The address comes first. Of course. There we go. Now I should be able to, let's just run it. That now should work. Yep, we're good. We are good. And now do we still want to print out the sum of the memory again? What is the sum of all the values in the memory? Yep. Got an answer. Let's maybe just print it out as well. Just to have a look. You never know what. Although it's going to be almost impossible to verify, isn't it? Let's just do it. And pray. Pray to the gods of the advent of code that the answer is correct. That was a lot more fun than yesterday. Thank you for watching.